Hello everybody, welcome to the Institute. This one is a check your understanding question. So it's another Newton's second law problem, and it stems straight from the sample that I just got done doing, but I want you to pause the video, look at what I have on here, and see if you can solve it before you actually see me solve it. So that'll make it a little bit easier. Now, one of the key things, if you notice on here, we're talking about the same soccer player that we had before. So they say described above because I got this from a book where those two were right after each other. So this is still, she has a mass of 70 kilograms. So the mass is still the same, but now notice that she notices that the ball is in a position to be stolen if she now experiences a force of 126 newtons to attempt to steal the ball, which is 2 meters away from her. So the idea is she's going to push off and try to head to get the ball away from somebody else. So that's the idea of this particular problem. And we're going to try to find time. So we're going to try to figure out what t is. So I would pause the video, try this problem out, see if you can figure it out. It's a kinematic and Newton's second law problem, and then come back. Okay, you're back, so that tells me that you've solved this problem. Let's go through what we have. So I'm going to draw this out again. So here's my little soccer player. Actually, I'm going to do this different this time. I'm going to do this as kind of a classic free body diagram. So my soccer player is a box. They are on the ground, so there is gravity pulling down on her. That's our force of gravity. We even talked about this already. She's 686 newtons in a weight. Force of gravity is the same as weight, but there is a normal force acting upward on her. That's the force that's perpendicular to the ground that pushes back whenever you come into contact with objects. If you sit in a chair, if you stand on the ground, if you push against the wall, the force back on you is what we refer to as a normal force. It's kind of like a reaction every time you touch something, a little bit of Newton's second law. Since I'm assuming she's not going to go up or down, she's not jumping in this case, these two are just going to equal each other, and this would be 686 newtons. The only reason I know that is we are not looking at acceleration upward. She's going to take off again. So it says she experiences a force of 126 newtons to attempt to steal the ball. So the idea is there's going to be some kind of propelling force on her. This time they give that to us. That's 126 newtons. I'm going to assume it doesn't say it in here, but we had it earlier, that there's no air resistance, there's no basically resistive forces slowing her down, so that's going to have her going. So the idea is the soccer ball is somewhere over here, and we're going to try to see if we can get to it. If I do that, and I mentioned that it's 2 meters away and how long, that type of thing, what I'm going to actually start off with is this propelling force should equal the mass of our soccer player times acceleration. So let's figure out her acceleration first. So her acceleration should be equal to the propelling force divided by mass. This propelling force is 126 newtons. Her mass is 70 kilograms. Newtons per kilogram is the same thing as an acceleration unit of meters per second squared. So 126 divided by 70 gives us 1.8 meters per second squared. So that's Newton's second law. That's not what we want, but that's a step in the right direction. So that's an acceleration. The next step is to take this acceleration and think of our kinematic equations. We know acceleration is a change in velocity over time. So your first instinct might be, hey, let's use that. But if you notice, I don't have a velocity. I don't know anything about her. I don't know if she stopped, if she's moving, what exactly I have going on. And it just mentions that she now notices that that ball is in a position to be stolen. And it says that she stops after completing the play described above. So if I kind of grab that, that tells me actually that her initial velocity is 0. So that was kind of a trick. I do actually know one of the velocities, but I don't know a final velocity. So I don't think this is going to be my best bet. I'm going to look for something else that has some kind of displacement in it. So this 2 meters, I'm going to do everything horizontally, so I'm going to treat this 2 meters as going to be my x. It's going to be a horizontal displacement. Do I have anything that has x, vi, acceleration, and time in it? So I do actually have that. I have the idea that the horizontal displacement equals the initial velocity multiplied by time plus 1/2 the acceleration multiplied by time squared. So this should hopefully allow me to find that information. But I don't actually want to find the displacement, I want to find time. Now my first instinct here is this looks like it's going to be quadratic, but notice that I have a VI of 0. So a VI of 0, VI times t, this whole thing is going to become 0. So I don't have to worry about it. I can just kind of cross it out. So x equals 1/2 at squared. If I multiply both sides by 2, that's going to get rid of my 1/2. I can divide by an a. Get rid of the acceleration, and then that's time squared, so I'll have to square root this to figure out my time. So to figure out the time to get to that soccer ball, we're going to take the square root of this entire quantity, 2 times x over acceleration. We just got done using this equation. This was a great one if we wanted to figure out the time it took to fall some vertical displacement y, and then we put an acceleration of 9.8 in here. Now we're actually just using horizontal stuff. So to find this, we're going to take the square root of 2. We're going to multiply by the displacement of 2 meters, and then we're going to divide by the acceleration we just found, which is 1.8 meters per second squared. Pull out my handy dandy calculator. I'm going to take the square root of, let's see, my calculator's being silly. Basically, it's going to be 4 divided by 1.8. Hit enter, and I get 1.49 seconds. So about half a second, or 1.5 seconds to get to this soccer ball. And that is a great extra example of using Newton's second law. I hope you enjoyed, and I look forward to doing some more work at the Hinstitute, the Hinnon Institute of Physics.